So welcome. This is our system on alternating circuits, and there's really three bits to it. There's one bit which is basically how do we talk about alternating circuits, alternating currents, and then the next bit or voltages, whatever, alternating signals, and then the next bit is we're going to talk about how do we put specifically a capacitor, an inductor, and a resistor together to make a tuning circuit. Then the last little bit we'll talk about are capacitances, and this is important stuff. So let's begin with the first bit, sources of AC. AC just means alternating current, but it applies, you can have an AC voltage, alternating current voltage. It's just AC means alternating. And we can talk about phasors. So, okay, the diagram on the left is the, if you like, the waveform. It basically shows the voltage versus time. And we've got a sine curve. And that, if you think about it, comes out of the fact that we're spinning a coil inside a magnetic field. And so if you imagine spinning the plane of a coil, the area is going to form a sine curve, its magnitude. So we get a nice sine curve. We know how to deal with sine curves. There's a mistake on this diagram, so let me correct it. I correct it every semester. I keep meaning to change it. So the other way we can represent a cyclical pattern, which we learned at the very beginning of simple harmonic motion. Remember, simple harmonic motion gives you a sine relationship. So the very next thing you can do is you can say, I'm not going to do this continuous sine curve. I'm going to have a continuous circle. So I start here at that point, and then I go around, and I'm not quite at the 90. Let's say I'm at the 90 degrees. The 90 degree point will be there. And here's the 180 degree point, which will be there. And here's the 270 degree point, which will be there. And then I'm back here, which is now 360, which is there. And then I go on to 360 plus 90 is 450, which is there. And the nice thing is I can have this thing just repeating over and over again, rather than going on and on across my page. So this is a phasor diagram. This is a wave diagram, if you like, or a signal diagram. I've got a mistake here. So I said, let's stop the process here. And at this point in time, I had a signal which is like that. That's my voltage. And that actually, if you take this line across, is there. That's not right. This is after the 90 degrees, whereas clearly the point of interest I had was before the 90 degrees. And I could turn around and say this happens after a certain time, which is only useful if I can compare it with the period of this wave. Agreed? Or I can turn around and say this happens after a certain phase angle, and I know for all waves one period as a phase angle of 2 pi. So in some ways this is more valuable to us, which is why it's useful. Nothing in your book is there because somebody likes it. It's there because everybody finds it useful. So then B would be round here somewhere, and then C would be down here somewhere, and then D would be back here somewhere. So we swip backwards and forwards. Sometimes we find the actual original diagram more useful. Sometimes we find the phasor diagram more useful. EE people tend to like the phasor diagrams because they are useful. So there's a little bit of a learning curve with that. Just you've done it before. You did it with oscillations and waves, but you've got to go back and repeat it because now we're using it in a very serious fashion. When a loop of wire rotates in a magnetic field, that's how power stations work, for example, then the voltage is, my little voltage at a given time is equal to my maximum voltage times the sine of the angle, and the angle depends upon the angular frequency times the time. We've been there before. And I know that omega is equal to 2 pi f, so I can talk about this in terms of, I could have, rather than sine omega t, I could have sine 2 pi ft. In fact, that's the way that it was introduced to me. It was 2 pi ft, and then we learned that 2 pi f equals omega, equal to omega. And omega, because f equals 1 over t, omega is equal to 2 pi over the period. So it's important that you go back and you just get yourself familiar again with that circular motion, simple harmonic motion, mathematics. So you're not kind of going, what is this? You kind of remember it.
If you replace the omega with the 2 pi f, aren't you looking for an angle?
What is omega? It's an angular frequency.
It's angular frequency.
So many radians per second as you go around this loop. Okay? So it's a radians, where's my pen gone? It's a radians per second, yeah? And you're going to multiply it by a time, omega t. So that's times seconds equals radians, yeah? Okay. And 2 pi f times t. Let's have a look. I'm taking frequency, which is 1 over seconds, times time. That cancels out. And I end up with the angle in degrees. So it's the same thing. It's the same thing. Okay. Yeah, cool. I didn't explain that very well, but it's the same thing. Problem you get is you have, when you average something which is oscillating, the answer is 0. It's always 0. If it's a plus or minus 1 volt, the answer is 0 for the average. If it's plus or minus 1,000,000 volts, the answer is 0 for the average. Because it spends as much time being positive as it does negative, so it always averages out to 0. That's very deceptive, because if you were to connect yourself to a 1 volt AC supply, you'd have a very different outcome than if you connected yourself to a 1,000,000 volt AC supply, and yet the average is the same. So clearly we got to figure out a way of avoiding this problem of the average. We got to find a way of representing how much stuff is there. And the way you do it is you say, well, the curse of this is that we have a positive bit cancelling out a negative bit, and a negative bit cancelling out a positive bit. Okay, well, let's get rid of all the negative bits. So you square everything. That's an easy way of squaring everything. And then what you say is, oh, well, let's average that. So you get the average of the squared bit. And then let's undo what we did by square rooting it. Oh, now we have the square root of the averaged of the squared bit. And it works out pretty good, actually. We clearly, if we take the peak, we say, well, let's just characterize it by the peak voltage. You're only at that peak voltage for an instant. So it's not really representative. If I had an AC voltage causing an AC current going through a resistor, and I try to characterize the power dissipation using the peak voltage and the peak current, I get an inappropriate number. Because it's only at the peak voltage for an instant, and it's only at the peak current for an instant. So I have to find a way of getting a number, which when I multiply that number of voltage times that number of current gives me a true reading of power. And this is the way you do it. Yes?
Why not just use absolute value?
Yeah, okay. But this was done before they did all that. This is traditional, you know. But absolute value of what? Of the voltage in time, yes, it would do the same thing. But then you'd have to average that. Yeah. Well, that takes a computer. So what they do is they say, okay, what did I do? I squared it, I meaned it, and I rooted it. Yep. Okay, so let's call it RMS. And they flip the order. I have no idea why they flip the order of, you know. But this is called RMS, root mean square. It's very useful when you get things that are, you know, symmetrically changing, root mean square. So consider a plot of current versus time. The average value for the current over one cycle is 0. That's a real problem. A 0 average current implies no current, but this is incorrect. It works for voltage as well. I'm just using examples here. It is better to use the root mean square. RMS equals the Imax over square root of 2, which equals, so what I remember is my I RMS equals 70% of my Imax, and that's my figure of merit, 70% of it. I voltage, my VRMS equals 70% of my Vmax. You can work in RMSs as if you were working with DC signals. The math all works, your circuitry all works. So you can take an AC signal, AC circuit, which does not have, so with resistors, and I can look at the power dissipation just the same way I'd look with DC signals, DC voltages and DC currents. So IRMS is 70% of Imax, and my VRMS equals 70% of my Vmax, and P average equals delta VRMS times IRMS. You can't use your peak value of your voltage, and you can't use your peak value of current, because you're only at that for one instant. This RMS value is the averaged value. It's the time average value, ignoring the polarity. So an AC current has an amplitude of 10 amps. What is the RMS current? So I say IRMS is equal to, what did I say? I think I said it was Imax over the square root of 2. Was that right? Which equals 0.7 times Imax, which equals 0.7 times 10, which equals 7 amps. And an AC EMF has a amplitude of 15, so VRMS is equal to Vmax over square root of 2, which equals 0.7 times Vmax, which equals 0.7 times 15, which equals 70 plus a half of 70 is 105, which would be 10.5 volts. So there's my two answers. Just a nice, simple conversion. People do it a lot, so be used to it.
What was the final answer?
10.5, I think. Yeah, 10.5.
Is it acceptable to use 0.7?
I use 0.7. Yeah.
So like on the test, it would be acceptable to use 0.7
Oh yeah,
rather than the square root of 2.
yeah, I use 0.7. Yeah. It's just in fact I always have to remember it's square root of 2. I just know it's 0.7. I mean, it's like, it's near enough. Maybe electrical engineer would like be pulling their hair out, but Okay. Resistors in an AC circuit. So let's take our three components and we're going to put them together. We're deliberately doing this because we're going to make a tuning circuit. So here's my schematic. I have not a battery, but I have this little wiggly thing in a circle, and that means an AC source. Could be mains, could be a function generator, could be a whole bunch of things, but it's going to give me an AC source. I need to know how this voltage applied changes in time, and so we have delta V equals delta V max sine omega t. I'm deciding to start it off like that, sine omega t. Notice, I'll emphasize this, in some books they go 2 pi f times t, and that's the way they start off, and it's just, I find it easier to work with omega t. Okay, so then we have resistance R. So the EMF is dropped across the component, so that's my potential difference. My potential difference is R. I can plot a graph using a oscilloscope of time, and I can have current in blue and my instantaneous voltage in red, and so both of them, when you get no voltage, you get no current, so both of them start off at the 0 line. When I get maximum positive going voltage, I get maximum positive going current. When I get no current, I get no voltage. When I get maximum negative going current, I get maximum negative going voltage. They're in phase with each other. That looks very simple to interpret, doesn't it? It's very nice. But we'll find out later on that this is the easy case. And this is where the phasor diagram comes in. Phasor diagrams are really good at comparing complicated signals. So although this looks very interpretable, they're both maximum, they're both minimum, different sizes, but they're a ratio of each other. It's very straightforward. It's not always going to be that case. I prefer to pick a point in time, so I'm going to pick a point like that. And I'm going to represent that over here. And so what I have is I have a phasor diagram, and I have a little red dotted circle and a blue dotted circle. And the red dotted circle is the extreme point for my phasor for voltage. And the blue dotted circle is the extreme point for my phasor for current. And if I pick any point in time, I can tell you that these two arrows will be in line with each other, and one will always be bigger than the other. If I take this point here, that point dashes back, and he's there, and that point actually is there, and that point dashes back, and he's there. So that bit there is that bit there. So, and what I can say is for this, my current equals my voltage over my resistance. I equals V over R. That's the way I get the ratio between these two things, yeah? I equals V over R. Ohm's law. That worked nicely. Let's see if we can do that same analysis for... Oh, I missed one thing out. I didn't do the math. So, using Kirchhoff's loop rule, we say delta V minus, so delta V, which is on this side, minus delta VR, which is the voltage drop across my resistor, equals 0. That's his loop rule. And delta VR equals delta V max sine omega t. We know that because that's how we designed it. So my current equals delta V max over R times sine omega t. Oh, interesting. And that, of course, is my delta I max. So my I max sine omega t. So what I see is sine omega t for voltage gives me a sine omega t for current. That's going to be important. We're going to look at that. So now let's look at an inductor. No resistance, just inductor. And I say, well, okay, we have Kirchhoff's rule. The voltage that's created as an EMF is spent as a potential difference, time varying in this case. My delta V equals minus, my delta V and my potential difference across my inductor is minus L di by dt. In AC, the tradition is you don't use big I's, you do little i's. So that's not an imaginary number. That's not D imaginary. That's just DAC current. And I've got mixed feelings about it, but that's what the world's doing. So delta V minus L di by dt equals 0. And then remembering the delta V in time, so my voltage at any time is equal to V max sine omega t. That's my power supply. I'm defining that. I'm choosing to say I start off and I go like that, rather than I go like that. So that's me, that's my choice. But having chosen it, let's shove it into the system. And I say, well, then L di by dt equals delta V max sine omega t. Di is equal to delta V max over L sine omega t dt. Integrating I is equal to dV max over L times the integral of sine omega t dt. The integral of sine omega t dt is cosine omega t. So IL is equal to minus dV max over omega L cosine omega t. And if you remember that cosine omega t equals minus sine omega t plus, minus pi by 2. So I end up with IL is equal to delta V max over omega L sine omega t minus pi by 2.
I'm sorry, the I is the current?
I is the AC current is called little I.
AC current is little I?
Yeah, the symbol for AC current, so you know it's AC. Is
And the
little I.
is the I capital is the regular current?
There's no I capital on here.
I'm saying like for the other
Yeah,
side.
we were talking DC before, yeah.
There, some capital I is always there, right?
So it's like writing, okay? So there'll be times when you're talking about AC stuff and you want to emphasize it's AC stuff, so you put little I down. There'll be other times when you're talking about DC stuff and you put big I down. You know, if you put down big I for an AC current, no one's going to kind of like, you know, commit seppuku or anything. They're going to say, okay, they just put it down. So don't,
Only if it's
you know, it's
previous
just
year.
contextual, you know. It's like, and I can't guarantee in my entire thing. I'm going to use little I throughout, but that's what they tend to do that's what they tend to do to emphasize this is AC, but it's kind of like it's speaking. So don't get tied up with the letter so much.
It's a language.
Look at the principle of it. The important thing is not that letter. The important thing is this mathematical term at the end. And what we found was two things. We found we had a sine here, became a cosine there. So there's a phase difference. That's like really important. And we can even figure out how much the phase difference is in angular terms if we recognize this, that the cosine omega t is the sine of the original angle plus this constant, this phase angle. And the phase angle is pi over 2, which is 90 degrees. So there's not only a phase difference, there's a 90-degree phase difference. And then the second, so we'll talk about that first of all. So now if I use my oscilloscope and I have my original driving voltage in red, and now I look at my current, what I've got now is that the peak of the current is behind the peak of the voltage. Because of this mathematics which leads to this 90 degrees phase. And there's also a difference in the heights. Yeah. So I can account for the shift in phase by this cosine becoming a sine. This sine creating a cosine. And I can go from the cosine back to a sine and see the angle. So the mathematics tells me, oh yeah, when you apply an AC voltage to an AC to an inductor, you're going to measure current which is 90 degrees out of phase. That seems weird. When you get your maximum potential difference, you don't have your maximum current flowing because it's not a resistor. It is a inductor. And then the second thing is this ratio. And this ratio, if you think about it, if I take that value there, just forget about, this is a modifier. This is like what happens in time. But if I just pick the peak values, then what you see is my AC current is equal to delta V max over omega L. And what we said before was that my current was equal to delta V over R. Can you see that? So, you can say this omega L is behaving just like that resistor did there. That resistance did there. It's an analogous mathematical circumstance. So let's make this new thing called, let's not call it resistance, I don't know why they didn't, but let's call it reactance, XL. So XL, which is like your inductive resistance, is omega L.
XL is inductive resistance.
It says inductive reactance, which is like your inductive resistance, okay,
X large.
is omega L, okay? So two things came out of this. One was there's a 90-degree phase difference, and the current was left behind. And I'm going to change that. So the reason why they're saying the current was left behind was because you applied the voltage. I'm going to leave it like that. So there was a phase delay came out of this for the current, and there's a ratio between your maximum current and your maximum voltage, and you can get that by basically having this inductive reactance, omega L. And then you can use Ohm's law. V equals IR, V equals XL, V equals I times XL, It kind of works the same way. If I do the same thing for the capacitor, then we say, well, again, you know, our EMF is equal to our DC potential to our potential difference, and they got to sum to 0. So then we get one equals the other. And we do the same math. We say, well, our delta VC equals Q over C. And we say, well, we're going to apply delta V equals delta V max sine omega t. So delta V max equals sine omega t, which equals Q over C. So C times delta V max equals sine omega t times, which equals Q. Well, IC equals dQ by dt, which means that we have omega c delta V max cosine omega t. And if I, again, oh look, we went from a sine term to a cosine term. That's interesting. But now we say, well, cosine omega t equals sine omega t plus pi over 2. So if I want to express it like it was, IC is equal to omega c delta V max sine omega t plus pi by 2. So again, we have a phase jump, but this time the current is in front of the voltage. And there's also this ratio, and if I look at this, so forget about the modifier, I is equal to V over R. So remember, I is equal to delta V over this R kind of term. And for this, our R kind of term is that. So our R kind of term is not XC, not omega C, but 1 over omega C. Because it's over R. So R must equal 1 over omega C. For the same mathematical pattern. So what's come out of this? The two really important things. One is that there is a phase lag for the inductor for current, 90 degrees. There's a phase jump ahead for the current in a capacitor. And that there is a capacitive reactance and an inductive reactance that depend upon, that are analogous to resistance, but they are frequency dependent. They're frequency dependent. And if I, let's get a page here. If I plot this out, if I have frequency and I have my X, you know, X is going to be measured in ohms. XL, XC, doesn't matter. I know that XL is equal to omega L. Yep. Straight line. I know that X, change the color when you want to change the color. I know that XC equals 1 over omega C. Can you see? If I have a circuit containing both of these, my capacitance will kill me at low frequency. Because it's huge. It's a huge ohms. And my inductor is going to kill me at high frequency. Because it's a, not huge, but big ohms. And in between, I have a sweet spot. That's got the minimum amount of resistance. And that's going to be my omega naught, which is my natural frequency for this oscillating system. That's what we're about. We're about picking a value of C to give me, if I change the value of C, then I change the value of this guy. And if I change the value of L, I change the value of this guy. And it's picking that combination so I get whatever sweet spot I'm looking for. So that's the game I play. Now with an old-fashioned radio, you don't see them anymore. but there used to be a dial on the front. And that literally was connected to a capacitor. It was this huge capacitor which had veins inside. And as you turned it, you would cross those veins more or less. So you change the area of the capacitor. It's a very clever way of changing the area of the capacitor. And that's what you changed on that. Okay? So that's where we're going. So what's your job? Your job is, at this point, know that. And know that there is a phase change. Know that the current for a capacitor is current for an inductor is behind. No, the current for a capacitor is in front. And I'm going to give you a way of remembering that, which is this. If you look in the book, anybody got the book with them?
The what?
The book, the textbook. Anybody got the textbook? I didn't bring it either.
There is a book?
So, let's do these first. What's the reactance of a 5 Henry inductor? Have a go at those. So let's have a look at this. Let's put this on pause. So we're back. So what is the reactance of a 5 Henry inductor when 5 radians per second AC voltage is applied to it? So we're going to turn around and say my reactance is X, and it's of an inductor XL equals omega L, which equals omega, which is going to be my 5 radians per second. So that's 5 times my inductance, which is 5, oh dear me, that's 25. And that's going to be ohms. It's just ohms. I wish they'd called it inductive resistance and capacitive resistance, but they didn't, because it's frequency dependent, so they called it reactance. And I understand that, but it behaves just like resistance. And then what is the reactance of a 10 farad capacitor? So XC is equal to 1 over omega C, which equals, and this is going to be 1 over, and then I put it in hertz, didn't I? So, okay, omega equals 2 pi f, so 2 pi f times C. So this is 1 over 2 times pi times f is 54 times C, and C is 10. So that would be 540, 2 540s is 1080, so this equals 1 over 1080 pi, which is about 3,000, 1 over 3,000, which is about 3 times 10 to the, 3 times 10 to the minus 4, yeah. And that's going to be ohms. And then what is the resistance of a 10 ohm resistor at 25 hertz? I'm just trying to, lead you off a path here, because the resistance of a resistor is the resistance of a resistor. It's 10 ohms. Now, as with all things, it's, when things come and they're similar but they're different, you've got to distinguish between them. So between now and the test, you've got to make sure you don't get your inductive reactance confused with your capacitive reactance. And I'm a visual thinker, so I used to get it much more from the graph. I remember that really well. I remember that really well. Pardon? So I visualize it. I don't make the mistake. Remembering the two equations, I'm going to get them backwards all the time. So be careful with that. But that's, pardon? Yeah.
Yeah, you're not going to call them like capacitance or inductance. You're just going to say them. You're going to call them reactance. That's it.
I'm going to ask you, what is the reactance of a component?
So for us to determine which, if it's inductive or capacitive, that is.
Well, in an inductor as an inductive reactance and a capacitor as a capacitive reactance. I mean, it's no more complicated than that. Like the resistance is for the resistor, but they're behaving analogous to resistors. So now let's do the next bit. So you know that there's a phase jump, a phase difference between the applied voltage of the currents, and you know how to figure out what the reactances are. So now let's put it together. Now, if you look in the book, it probably says RLC circuits. And I never call them RLC circuits. This is my contribution to the education world that's gone unnoticed, Because if you think about it, if one's always in front and one's always behind, then put them in the order. So you need never have to figure that out again. So I choose to call them LRC circuits because L in most calculations comes first and C in most calculations comes last. But we learned that the current in the capacitor was in front and the current in the inductor was behind. So what's going on? When I look at that circuit, it's a series circuit. And even though there's a capacitor there, we can picture it as a AC current flowing through it, yes? Currents don't flow through capacitors, but AC, you can imagine AC current flowing through it. Yeah. And the one thing I know about AC circuits is the current is constant in all those devices. The voltage is not, but the current is constant. So, okay. That means that rather than talking back here about how the current was in phase with the voltage, how the current lagged the voltage, how the current preceded the voltage, I really would have been better off saying, oh, here the voltage matches the current. For the inductor, here the voltage is ahead of the current. Here the voltage is behind the current. Now, they don't introduce it that way because the experiment is you apply a voltage and you look at what current comes out. But when you put these three things together, it is the current that is constant. So we kind of switch it around. And again, this is learning it. It's kind of going, I'm going to go, oh yeah, the voltage across the inductor is always 90 degrees ahead of the voltage across the resistor, which is always 90 degrees ahead of a voltage, which is 90 degrees ahead of a voltage across the capacitor. So, and I look at this, and man, this is disastrous. I mean, this is what's going on. So the voltage across the inductor, there's its peak, is 90 degrees ahead of the voltage across the resistor, that's 90 degrees, which is 90 degrees ahead of the voltage across the capacitor. They don't even put these in the right order, yeah? But to see that is really hard. There's my peak, and then 90 degrees later comes my peak in my resistor, and then 90 degrees later comes my peak in my capacitor. L comes first, then R, then C. L comes first, then R, then C. Okay? Representing it like this is nasty. We need phases, and that's where we're going to go. We say consider a series network consisting of resistor, inductor, and capacitor. The current at all points in the series AC circuit has the same amplitude and phase. The, not he, the instantaneous voltages are out of phase with each other. So delta VR equals I max times R, delta V. There's the magnitudes of them, but there's a phase issue as well. Okay? So there's the size of these guys, but there's a phase issue as well. Delta VR is equal to I max R sine omega t. Delta VL equals I max XL sine omega t plus pi by 2. Delta VC is equal to I max XC sine. So this bit is telling you the phase relationship, and that bit's telling you the size relationship. How big it is, size. Now, the one thing we got to know is, just as we know from simple circuit theory, that the current flowing through all these resistors is the same, all these components is the same, we also know that the potential differences across these components at any instant must add up to the EMF. But there's a problem, because the EMF is sometimes zero. And at that instant, we don't get zero voltage in all these components. And the reason is that these are vectors in phasor space. So we're adding them up vectorially in phasor space. And so we're doing this. We're going, oh, look at this. My delta VL is 90 degrees ahead in phasor space of my delta VC, of my delta VR, which is 90 degrees ahead of my delta VC. Because it's in phasor space. So, yes, I can get a zero value, because two things that are non-zero oppose each other. So I'm not arithmetically adding them up, I'm vectorially adding them up in phasor space. So I say, well, what's the voltage at any given instant? Well, it's going to be, use Pythagoras, because XL, so delta VL and delta VC are fighting each other. So they will always combine to give you one component. And that will always be at 90 degrees to the voltage across your resistor. And so we'll end up with a resultant. And that resultant, which is a certain value dependent upon Pythagoras and a certain phase angle. So, okay. Which means, and this is the skill, which means that I can represent this as a phasor diagram in impedance. So what I have, what I picture is my XL and my XC and my R. And I combine these guys together, so this is going to be XL minus XC, and this is still going to be my R. And I combine these guys together to give me a Z value and a phase angle. That's the skill. The skill is, given an LRC circuit and a frequency, can you work out XL for that frequency? Can you work out XC for that frequency? Can you work out R for that frequency? Can you combine them in a phasor diagram to get the impedance for that circuit, which is the overall resistance? And can you work out the phase angle? The Z, if I think back about it, the Z, where did I put it? I hid it somewhere. The Z is the sum, the vector sum of these guys. So there I drew them, and I was like, there's a minimum here, The Z, I'm cheating on that, I'm adding them up arithmetically. It's a cheat. But you get the idea. There's this natural frequency. There's pass frequency. And the pass frequency is when you get a minimum Z. Yeah? Minimum total resistance effect. So the skill is, given a simple LRC series network, Can you work out what the XL is? Can you work out what the XC is? Can you work out what the resistance is? Can you combine them to form a impedance, a Z? And can you combine them to form to find a phase angle? So this is a really important diagram, although this is the better diagram down here. This is the thing that you need to take home because that shows the effect. This is how you get that. And we know from Pythagoras, again, the book's making another equation for you to learn, but you already know this equation. Z is equal to the square root of r squared plus the sum of these two. Well, the one's negative, so the difference of those two squared. And we know that our maximum current is related to the maximum voltage and the Z using delta Z max is equal to I max times E. And we can work out our theta angle by basically saying it's the opposite over the adjacent. Okay, 10 to the minus 1. Let's do one. I got to put my thinking cap on a little bit because I want to make sure, I'm going to try and make the numbers come out reasonably well. So again, get into the habit of why not just draw them in the right order so that you reinforce this LRC system. And I'm going to say that that is about 20 Henry. And I'm going to say that this is about 3 millifarads. And I'm going to say that this is like maybe 6 ohms. So I want to know, so a question I could ask you is, what is XL? Well, XL is equal to...
We need W, right?
Sorry?
We need the frequency?
I'm not for XL. XL is just a value. Oh, I'm sorry. You do need the frequency. What is XL at? You're asking me to commit to a frequency now. I'm just going to commit. Let me just think for a second. So that is going to be LC. So it's going to be that. I'm going to say 3 radians per second. No, let's say 5 radians per second. At 5 rad per second. So XL is equal to omega L, which equals 5 times 20, which equals 100 ohms. So at this frequency, that's 100 ohms. Yep. XC at 5 rad per second. XC is equal to 1 over omega C, which equals 1 over 5 times 3 times 10 to the minus 3, which equals what? Can somebody work that out for me, please? 1 divided by 5, enter, divided by 3 second, EE minus 3, which equals 66. 66.6 ohms, 67 ohms. Okay? And I'm going to cheat. I'm going to make this one 60 ohms. I'm changing my resistance to 60, so it's about the same size. Yeah. Problems with these? No?
Is that a 67?
That's a 66.6, so I made it 67, yeah. Okay, so find Z. Find Z, yeah. Z. So XL is 100. XC is 67. And that's 60. So this is going to give me, and you know, I'm just going to go and say, oh, that's going to be 33. That's 60. So I'm going to say Z is equal to the square root of 33 squared plus 60 squared, which equals 33 squared plus 60 squared equals that. Second square root, second answer, 86. I'm getting 86. 68, not 68. I'm dyslexic as I go on. Yep.
Where do you get the 33?
So that's 100 ohms
Where do you get the
pointing upwards, and that's 67 pointing downwards. So add them together, call that positive, call that negative. Yep, difference between the two. So I don't even bother. You know, the book says that. It says square root of r squared plus xl minus xc squared. You can do it that way if you want, but I'm just doing it here. I'm just doing it because I'm thinking about it. I'm not just using a magic formula. You know. And what's my phase angle? My phase angle, tan to the minus 1 of, sorry, the phase angle equals tan to the minus 1 of the opposite over the adjacent, which equals 33 over 60, which equals second tangent 33 divided by 60. That's going to be 28.8 degrees. Okay? Yes.
XL is always going to be greater than X.
Oh, no, certainly not. No, certainly not.
So sometime then, all right.
So sometimes,
You're gonna get a negative. Oh, yeah.
So if that happens, then we have to, the angle's going to be plus.
could be a negative angle. That's going to be
Negative angle.
either very big or a negative so and so, yeah. And again, if you're looking at your diagram, it's a piece of cake. If you're trying to do it through just the equations, then you've got to keep, you know, signs into account and all that kind of stuff. But if you're looking at your diagram, then you know, oh yeah, that's going to be that, and that's going to be that. So dum, 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 dum. There's my z, and then phase angle's there. Yeah. Oh, really, the phase angle's there, but I can call that a minus that. Yeah. Cool. That's the skill. That's a very typical test question. That's what I want you to know. Okay. There's a little bit more to it, but that's basically in essence, that's the thing. So practice that. Let's go here. Let's talk about these. Just a couple more things. In fact, I want to I'll just do it in order. So the power in AC circuits, no power losses. Just let me have a quick check. Oh, I've got to stop in a minute. So no power losses are associated with pure capacitors and pure inductors. It's only resistors that have power losses. Power is converted to heat, so we can say for an RLC circuit, then we have power is equal to this. And if we remember that and we substitute, we end up with our power equals I squared R, where I is an RMS. And we did that before. We just said we got to work in terms of that. Bum, 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 bum. And I'm okay with that. And then we have different resonances. So here's a situation where they've plotted out the solution for different frequencies, for different values of resistance. And what you find is for a low resistance you get a very nice sharp peak, but as the resistance of the resistor gets bigger, you get a more rounded peak. This is really good at separating out radio stations, because the one that you're tuned on will get a big signal, but the ones that you're not tuned on will get a very small signal. Whereas this is not so good, because the one that you're tuned on is not that much bigger than the ones that you're not tuned on. So discrimination is better as R gets smaller. We say a series RLC circuit is said to be in resonance when it has a maximum, when its current has a maximum value. The RMS current is I RMS over delta V RMS over Z, so we can figure that out. The impedance and current depend upon frequency. At resonance, what do you know about resonance? The XL must balance the XC. They're not zero, but they're balancing each other. And so we can plug in and say, well, XL and XC must equal to each other. So omega L must equal 1 over omega C, but omega's got to be the same when they're in resonance because it's the same frequency. So omega naught equals 1 over omega C. That's an important thing to know. I will ask you about that. What is the resonant frequency for this? So can you find that? What I'll do typically is I'll give you a circuit. I'll ask you to find this. And then I'll go a little bit away from it and ask you to find me the impedance and the phase angle when you're nearby but not at. That's what I'll do. And then a couple of things for more engineering, really. The power of resonance, basically, how do we characterize it? We take the full width at half max. So we say, basically, we say there's a quality factor called Q. Q equals my resonance over my half max resonance width. And that turns out that equals omega naught over times L over R. So I can play games. If I pick a nice big value of L and a nice small value of R, I can get a sharper peak, better quality of tuning circuit than if I don't. So we play games with that. Last little thing. Do I have time? Last little thing. Basically, I'm going to stop the tape, but just recognize that there's mutual inductance for transformers means that we have a ratio, and the ratio of what I prefer to think of it is the ratio of the number of turns is equal to the ratio of the voltages, and everything else follows from there. Okay, I'm going to stop the tape now. I got 2.5 minutes. N is the number of turns. So if I have more turns on N, and if the primary is more turns than the primary has more voltage than the secondary. So I remember this. The ratio of the number of turns is equal to the ratio of the voltage. If you ask me about the currents, I'll use V equals IR and be able to get it from there. Or I'll use power, actually. Okay. Cool. I'm going to stop there.